and J, or N1 and N2 itself, an inertial frame. Any question about that? So, starting from this equation, you really don't need to know anything from before. You don't need to know Newtonian mechanics, and you don't even need to know the two lectures in analytical mechanics that have been given. You need to know them to be aware of the bigger picture. To solve a problem in your homework or exam, for your luck, if you start with me now fresh, applying this equation, you really don't need anything else. So if you didn't study any single lecture so far, you can start fresh now. Okay?
You say that every single lecture.
not every single, maybe every couple. Yeah, that's right. And this is intentional. So, okay, I have Q1 is maybe R and Q2 is theta. Any question about this? You have to start the problem correct, otherwise the whole problem will just go away. Any problems assessing the number of degrees of freedom in this problem? Okay, I have a single mass, so here is my position vector. It's as simple as this. It's R. I'll even make it simpler. So here is ER and E theta. So it's R in the ER direction. You can make it R cosine and sine. It doesn't matter. Okay? And you have R dot is what? It's simply R in the ER direction, and the R is variable, so differentiate in your own frame. Plus omega cross, this is the very well known R theta dot, the tangential velocity. This is really very easy to get. The velocity is not that hard, usually. But what is a little bit tedious is to get the next step, which is the acceleration. Luckily, we don't need it now. I'm done. Position, velocity, please give me your kinetic. It's just 1/2 mv squared. Please, v is a vector. V squared, you need the square of that vector. So each component squared, add it together, right? R dot squared plus R squared theta dot squared. This is your kinetic, your potential. What about the potential? I'll give you some time to write. Let's do it fast. What's your potential? What's your potential? Come on. Yeah, the spring 1/2 K, the displacement squared, so your R minus the initial length. Any other potential force? Gravitational, you need mg. I mean, if the mass is, you need to choose a datum just to prevent confusion. Okay? To get the potential due to gravity, you need to choose a datum. Choose it wherever you like. Maybe the bottom point or this, but it has to be some fixed point in space. Okay? And from this datum, just measure the elevation. Positive upward, negative downward. That's it. Okay? Maybe we choose this as a datum. And now the position at any theta will be negative, right? R cosine theta. So this is negative mg times the elevation, which is R cosine theta. Kinetic and potential, immediately I get my Lagrangian, simply subtract them together. So R dot squared, R squared theta dot squared, minus your Lagrangian. So this is plus. And from this magic red line, I will derive the two equations of motion immediately. So the R equation, please pay attention here. I'll give you some time to write. The R equation, here it is. Here is your equation. d by dt, partial your Lagrangian, partial your velocity, R dot. Talking about R. Minus partial rule Lagrangian, partial displacement, R, equals 0 because we don't have any non-conservative loads. That's easy. So d by dt, please differentiate your Lagrangian with respect to R dot. In this framework, R and R dot are different, theta and theta dot are different. Okay? To differentiate this as if it's a function of R dot. I only have one R dot term. R dot squared differentiate gives you 2 R dot, and you have 1/2 M. So you get M R dot here, minus partial L partial R, I have a lot of r's. I have 1, 2, 3. So minus, here is a bracket. The first term with respect to r is mr theta dot squared. The second term with respect to r, this is minus k r minus L naught. The third term with respect to r is simply mg cosine theta. This is equal to 0. So you can see it's as easy as this. I'm done, right? Because this is simply mr double dot. So this is the first equation immediately, and we're going to do the second equation similarly. Any question about that? So you really don't need anything about Newtonian mechanics, and certainly, as you see now, you didn't need the details of the last 2 lectures unless you need to know the global picture. So, the theta equation, please. Let's do the theta equation, and I'll give you time to write. What's the theta equation? Here it is. It's d by dt, partial L, partial u, theta dot, minus partial L, partial u coordinate, which is theta, equal to 0 on non-conservative loads. It's a piece of cake. So d by dt, differentiate this guy with respect to theta dot, it's only one term.
mr squared theta dot.
Very good, mr squared theta dot, minus partial L, partial theta. I have only one theta term here. So this is negative mgr sine theta equal to 0. Please do it carefully, because this is d by dt for 2 terms, and both are variables, right? So the first one is simply mr squared theta double dot, but you need the other term, right, which is 2 mr r dot theta dot. Any question about that? Take care of the differentiation. Sometimes we're differentiating with respect to r dot, then we're differentiating with respect to r, then we're differentiating with respect to time. So keep track of these, okay? And I'm done. Here's your equation. I got the 2 equations in motion immediately. Yes, you?
Good question. So when you took the partial of r, the r equation, there's r squared plus theta dot square, right?
R dot square plus,
Plus.
yeah, this was R dot square,
Oh, okay.
right? Coming from here,
Okay.
I'm copying this. So R dot has nothing to do with R.
Right.
So I don't care about this term. Now I'm differentiating this term with respect to R, right? So
Yeah.
this is 2R theta dot square.
Right.
Multiplying by 1 and having outside.
Right. And then the equation down there, there's no theta, the mr.
MR theta dot square.
Oh, okay, sorry. I
Yeah.
thought it was. Okay.
Yeah, yeah.
Thanks.
Any question, guys? Please, if you have any question, like I said, you can see it immediately. That it really doesn't depend on any of the lectures from before. You can really start fresh now. And actually, if you're going through a prelim exam, PhD, most of it is on, if not all of it, is on Lagrangian mechanics. So if you're going to a prelim, you might just come now and start fresh from here. That's it. Any question? So don't let it pass. If you literally know nothing from before, don't let it pass from you, please. Yes, Andrew?
I just had a general question. Let's say the mass is not moving, so it's oscillating. Would that be considered a non-conservative force?
The mass,
Like, let's say you pulled it, and now it's compressing the spring, right? Now QNC is not 0, correct? Or would it?
I apply a force.
Like you pull it.
Oh yeah, if I'm pulling it,
Yeah.
yes, we're going to do it immediately in a minute.
Okay.
Yes, this is a non-conservative. Any general force, the default is being non-conservative, and we get it from the expression. And even if you did a mistake, by mistake I mean the gravity. I forgot it's a conservative, although this is an exorbitant one. But anyway, it's non-conservative. Just apply the rule that we're going to get in a minute, or you can see it from here. No shame. It just makes you do more effort, right? Makes your life more harder. But the other way around is problematic. You will not be able to proceed anyway. I mean, if you have a P here, for example, I say, oh, this is a conservative force. That's fine. Get its potential, please. You got its potential and put it. It's good. Of course, you'll not be able to do it. You'll not be able to write a potential because it's non-conservative. If you could, then we would have considered it as conservative from the beginning. So no room for fatal mistakes. So this is why we don't need to pay a lot of attention in this framework. It's just turning the crank. Any questions?
So if the non-conservative forces are also not known, and we have got 2 equations and 3 unknowns, then?
Say that again, please. No. In dynamics, forces, applied forces should be known. Right? These are applied, they are not constrained forces. Constrained forces are unknowns, that's right. But we typically ignore them. Right? They don't show up here in this framework. Any question? Yes, Sancho?
And then last question is that for the velocity for the kinetic energy, here you had it in the ER frame, so that made it easy. If you chose to write it in the N frame,
Doesn't matter. Doesn't matter. You will get the exact same answer because it's the v squared is the magnitude of the velocity v. The magnitude of any vector is independent of the frame you write this vector in, right? So this is why it's good to work with scalar quantities. Okay, let's go a bit harder.